Hi! Our first lecture this week covers material from Lecture 16 in the Total Notes PDF online, and the information on Fermat factorization is not in those notes. I'll be putting a copy of these slides on our Moodle website. My goal for today is to get through factorization in relation to the RSA crypto system and teach how to use the Fermat factorization algorithm in that context. We've been talking about RSA for a little while now, but let me remind you, we're trying to use modular arithmetic to form a crypto system. So I've chosen some very large integer n, whose factorization is just two different primes. So lowercase p and lowercase q here are my prime factors of the modulus n. The plain text messages that I'll be encrypting in this system are just the residues mod n. So I have some way of turning the information that I want into an integer. There's lots of ways to do that, and I'm not concerned which way you are giving meaning to those integers. We're only focusing on the mathematics for right now. And the formulas I use will give me a ciphertext. They'll give me some other residue modulo n, so my set of all plain text messages and my set of all ciphertext messages are the same. The keys for this system are the units of z mod phi of n z. So I've got my modulus n, I've calculated the Euler phi function, and now I'm looking at the integers modulo this new number, phi of n, and of those I can use any residue a as long as it has no common prime factors with phi of n. So this will be my key space, the set of all such residues. The encryption formula that I use, I'll take a plain text p, and I'll send that to p raised to the power e modulo n. So e is coming from my key space. And if e is my encryption key, then my decryption key is just the multiplicative inverse of e mod phi of n. So I've picked my encryption key here to be exactly one of those residues that does have a multiplicative inverse. And this works because exponents mod n can always be reduced mod phi of n. So my decryption formula is going to be take your ciphertext C, raise it to the power D, and that will reproduce the plain text message. This is a public key cryptography system because I can publish the encryption key, E, without giving away what the decryption is. In that way, any person in the world can encrypt a message using this system as long as they know my key. But in theory, I will be the only person who knows the decryption key, which means that I will be the only person who can decrypt. So remember that I am publicly disclosing the modulus I'm using, which is n, and the exponent that I'm using, which is e. And then all the other parameters on this page need to remain secret. The prime factors p and q, the decryption key d, and the Euler phi function of n. To start out this lecture, I want to talk about why phi of n needs to remain secret. So bear in mind, if I am attacking this system, then I don't know the factorization of p times q. gives me n. I don't know that. But I can still approach this system knowing that the person who set it up chose an n to be the product of two different primes. So I know that my phi of n, or your phi of n if I'm the attacker, is calculated by taking phi of p times phi of q. That is our formula for the Euler-Phi function in terms of prime factorization. So that is p take 1 times q take 1. And if I multiply that out, I'll get n take p take q plus 1. Okay, so just arithmetic at this point. And if I rearrange, on the left-hand side of this equation, I've got both p and q. Those are the prime factors that I want to solve for. On the right-hand side, I've got n, which is part of the published information. I've got a 1, okay, I've got a 1, and I've got a negative phi of n. So if I'm an attacker and I learn what phi of n is, I can set up this equation and I can know exactly what number this right-hand side formula is giving me. Now, you might think that's okay, because this is an equation with some number that I've calculated and two unknowns. So if I'm trying to solve for two unknowns, I don't have enough information. Or do I? So, keeping the perspective that I know n, I know phi of n, and now I know exactly what p plus q is. I can actually leverage that information to solve for both of these integers. So, again, I know these three numbers. Let me take p plus q, which is a number that I know, and I'll square it. I don't actually know what the p and the q are, but whatever they are, the algebra has to follow this formula. I'll get p squared plus 2pq plus q squared. I'm going to take this number and subtract 4n from it. I can do that. I know what number n is. I know n factors is p times q. So subtracting 4n is subtracting 4 times p times q. Then I can cancel some terms, and I've got p squared take 2 times pq plus q squared. And wrap that all up. That's the same expression as p take q squared. So I know what p plus q is. I know what n is. With that information together, now I know what number p take q squared is. And taking a square root is easy, so I can take the square root of the left-hand side, and that gives me p take q. You can probably see where I'm going with this. So now I know n, I know phi of n. Those two together gave me p plus q, and those three together gave me p minus q. Well, then p is just these two numbers added together. That'll give me twice p. The q's cancel. Divide that by 2, and now I know what the prime factor p is. And I see a typo in these slides. This should be a minus. So if I had p plus q minus p minus q, the p's would cancel. I would get twice q with a double negative. Divide that by 2, and I get exactly q. So from these two numbers, I've recovered those prime factors which are supposed to be secret. Never mind, if I know what phi of n is and I'm an attacker, I can just calculate the decryption key directly. The decryption key is always the inverse of E mod phi of n. Fortunately for us, fortunately for the defense side, finding the Euler phi function of some very large integer n without knowing the factorization of n is just as hard as factorizing that n to begin with. The security in the RSA system comes from the fact that factoring large integers is very difficult and takes a lot of time, even with highly advanced computers. And fortunately for us, attackers would not be able to exploit this phi of n method that I've just described on the past couple slides. Something we should be concerned about, though, is, do I know that the factoring problem is always hard? It stands to reason that if I pick some random large number, then it should have just a random prime factorization. But maybe there are some numbers that are easier to factor than other numbers. How would I do such a thing? Or in other terms, since I'm playing defense now, how do I avoid those numbers? How do I avoid using an integer n as my modulus where factoring n is actually very easy to do? The method I want to talk about today comes from Pierre de Fermat. So, we need a lemma first, just to set the stage. You might be familiar with this one already. So this is just a small result to help build up the theory that I'm going to use. If a positive integer n is, So if a positive integer n is composite, then at least one of its prime factors has to be less than or equal to the square root of n itself. It's going to have at least two prime factors, since we're assuming n is a composite integer, and the proof is really straightforward. So let's suppose that every single prime factor of n is greater than the square root of n itself. Then I can unwind this and say n has a unique prime factorization, prime number 1 times prime number 2. Let's say there's k of these factors. Could be some duplicates in here. Each of them is greater than the square root of n, so that means that this product must be greater than the square root of n raised to the power k. Since n is composite, I know that k has to be at least 2. So this number here, square root of n to the power k, must be greater than or equal to n itself. Now, that's a contradiction because the left-hand side of this is saying we've got n. In the middle here, I'm saying that n is strictly greater than itself. And that is not allowed in the integers. So to avoid this contradiction, at least one of these prime factors in my list has to be less than or equal to the square root of n. So for an RSA modulus, I've got a pair of primes, p and q, and from that lemma, I know that one of these primes has got to be less than the square root of n, and the other of these primes has to be greater than the square root of n. I know that because they're supposed to be different primes. If n was just p squared, then I'd say that p is less than or equal to itself, which is the square root of n. Cool, not much to check there. But for moduli we would actually be using for RSA, we would have one small prime, one big prime, delineated by that square root of n. So Fermat's idea is, let's look at the formula for the difference of squares factorization. So this equation is always true no matter what x and y are. If you take x squared minus y squared, you can factorize that as x plus y times x minus y. So again, from the point of view of an attacker, I don't actually know what P and Q are, but I know they have to exist because I know that's how RSA encryption works. So I'm going to make it so that this is my P, x plus y should be my P, and then my other term here, x minus y, will be my Q. And that's not terribly hard to solve for. My x in this situation will be P plus Q on 2. My y will be P take Q on 2. Add them together, you get back to P. Subtract them, you get back to Q, just like we saw on the previous slide. That means, without even knowing what P and Q are, just knowing that they exist, the modulus n has to be equal to the difference of these two squares. N has to be x squared minus y squared. And here's the key idea. If P and Q are very close together, then y is going to be small, right? Y is the difference of these two primes divided by 2. And if this is a small number, then that's going to make n easier to factor because it is almost a square number. So n will be this big square P plus Q on 2 squared minus some little thing. N is almost a square. Fermat's idea says, let's take this expression, n is x squared minus y squared, and rewrite it. So here I've got the small number y squared, and that is equal to x squared minus n. And Fermat says, let's just guess an x and test it. We can just calculate x squared minus n, and maybe that is some perfect square. If we do land on a perfect square, then that means that I've got an equation just like this one. X squared is my guess, that's an integer, minus n. N came from the RSA system I'm trying to break. And now y has also got to be an integer. So we've got a solution for x and y, and then we win. So P is just going to be x plus y, Q is going to be x minus y. You might be concerned, how do I know that this thing, x squared minus n, how can I tell when that's a perfect square? Well, I'll just take a square root of it, and I'll check the decimal expansion that I get, and if it is an integer, or even if it looks like an integer, I can just re-square that integer and confirm that what I've got is the square root of this number. Very simple to do that. Okay, so this is what happens if we correctly guess our x. We get our factors P and Q. How do we make this guess, and how do we fix it if it goes wrong? For this algorithm, we're always going to start guessing with x equals the ceiling of the square root of n. So if you've not seen the ceiling functions before, this is just saying take the square root of n. If that's an integer, great, except it won't be an integer here because n is not a perfect square. If you don't have an integer, you round up to the next integer. So that's just the ceiling function. Smallest integer, no greater than square root of n. It's another way to say that. That's always going to be our first guess. If this guess does not work, we're going to increase x by 1 and try again. So fail, x goes to x plus 1, try again, fail, x goes to x plus 1, try again, fail, and you just keep on going until you find the x that works. And in fact, this algorithm will always work, eventually. So a key point is that eventually. But it works the best when y is small. So again, when p and q are too close together. In the long term, you'll eventually just get x equals n or thereabouts. I don't want to go too much into that, so you can just, for these purposes, you can trust me that it works as I say it does. Let's try factoring a very large number, well, a medium large number, let's say. N is 526,451, only I'm not going to tell you which factors gave me this n. The first thing I do is I calculate the square root of n, which my calculator says is 725.569. I can just double check that really quickly here. 526, 451, 725, and change, yes. My first guess is going to be x equals 726. I had to round up to the next integer. So I square my x, I subtract off, that's the wrong number. That is another typo. That'll be fixed on the online version of these slides. So let's do this real quick just to make sure I'm not pulling the wool over your eyes. Take this number, and that is what we are going to subtract from x squared. My x was 726, and I square that. I do get 625. So this is correct. This is a typo. Is 625 a square? If you have it memorized, that's fine. If you don't, we can just take a square root. So what is the square root of 625? Is 25 on the nose. So 625 is a perfect square. We got it in the first try. Again, my x is 726. My y is 25. So my factor p is going to be the sum of these two numbers, 751. My q is going to be the difference of these two numbers, which is 701. And both of those are prime numbers. I can quickly double check. 701 times 751 gets me back to 5,026, 451. And that's the factorization. It's something that we could have done, just pen, paper, and a calculator if we had to. So why did this work? My n that I picked, 526,000 and change, the square root of that n was 725.569 and the rest. My prime factors were 751 and 701. So you can already see that lemma is kicking in. One of them is less than that square root. One of them is greater than that square root. But they're really close to it. They're only off by, 25, 26. That's too close. Because they are so close together, it lets Fermat's algorithm find those prime factors very quickly. We didn't even have to do more than one step of the algorithm. Let's try another one, just as an example. I'll pick a smaller number to work with. My n this time is going to be 2,173. Step number 1, I calculate the square root of n. I get 46 and change. Step 2, I'm going to start guessing x's. My first guess is just going to be 47. I'm rounding up to the next integer. I calculate 47, take 2,173 gets me 36. And that's a square I've got memorized, so y is 6. I'm already done, again, in one step. You won't always do it in one step, but again, this is a very fast algorithm when your p and your q are too close together. What are those primes, p and q? P is going to be 47 plus 6, so I get 53. Q is going to be 47 minus 6, and I get 41. So just check 41 by 53. 2,173, just as promised. Now the reason I've gone through 2 examples of this is that I will be quizzing you on this algorithm on our next quiz. So be ready for that. But it's super simple. Step 1, square root. Step 2, x is the next integer larger than that square root. Square it, subtract n, get a number. If that number is a square, you're done. If that number is not a square, go up to the next integer x. If that difference is not a square, go up to the next integer x. And then step 3, how do I get my answer? The 2 different factors are my x plus my y, which was my square root here. The other factor is my x minus my y. Very simple stuff. Now, this is something that we need to worry about if we want to set up an RSA encryption. I want to make sure that my modulus n does not allow this attack to happen. So what do I want for making a secure crypto system, at least with the RSA method? I want 2 very large prime numbers, p and q. I want them to be very large so that n is too big to just factor by brute force. But now I've got another condition. I can't just pick prime numbers that are too close together. We've already seen if I pick p and q too close together, Fermat factorization just gets them very quickly from the publicly disclosed information. All you need is the n. How do I make sure that my p and q are not too close together? Well, I'll just pick some prime numbers at random. If I was just listing out primes in order, of course I'm going to be tempted just to pick the first 2 on my list, and those will always be too close together. So let's put in a random element and say, okay, here's some random number p that's prime, here's some random number q that's prime. Because I chose them randomly, whatever that means, the chances that p and q are too close together will be small. Okay, cool, but how do I generate a random prime number? Well, first off, I got to decide how big they're going to be. Let's say that I want prime numbers who have 1,000 digits each. Okay, cool. So I've decided on how big I want those numbers to be. I can just start generating random numbers that are that big. Earlier in the course, we've already been looking at number generators, random number generators, and we can do that using techniques of modular arithmetic, or we can sample random noise from out in the stratosphere. For today's lecture, I'm not terribly concerned with the method. We just have a way to produce random integers. But I need those integers to be prime. I'm not guaranteed to have a prime number when I use any of those generators that I've talked about before. So let's just generate numbers until I get a prime. Make a number p. Is it prime? Great. Make a number q. Is it prime? No. Ooh, how about another q? No, still not prime. Give me a third q. Ah, there, my third q is prime. Great. I just keep on going until I have two different primes. Well, that should raise another question. How do we determine if some random number is prime? Particularly if that number that we picked is so large, remember, we want big primes so that factoring is hard. If my prime or my proposed prime, my assumed prime, if the number that I want to be prime has been generated and is a very large number, I cannot just brute force factor that number and test, okay, 2 does not divide this number, 3 does not divide this number, 4 does not divide this number, and so on. Again, that'll take too long because of what we need these numbers for. We need them to be so large that factoring like that doesn't work. So in my next lecture, I'm going to start talking about tests which determine whether or not a number is prime. And I think I will leave it there for today. If you haven't already taken this week's quiz, it is on our Moodle site. There is no time limit, and you can take that at any point that is convenient to you. I do intend these quizzes to be about 15 minutes long, but just in case there's any technical difficulties, or if I've made the problems too difficult for the online version of quizzes, I wanted to make sure that nobody times out in the first online quiz that we've done. You can use a calculator, but you can only make one attempt at that quiz. So if you want to review last week's lectures and take that quiz, great. If you feel like doing it already, that's cool too. And I'd very much appreciate it if you took the survey afterwards just to let me know how much time it did take so I can know that I'm setting the bar at the correct level for online quizzes. All right, that's it for today. Thank you for dropping in. Catch you later.